Hello everyone. In the last video, we looked into the NMOS and PMOS, or basically CMOS as a whole device from a short circuit and a capacitance and a load capacitance point of view. Let us try to look into in this video into the NMOS or the PMOS, or in that case the complete device from a leakage current point of view. So when we say a leakage current, it's basically a current that flows when your device turns off. So whenever your VGS or the gate to source voltage of your NMOS goes more than threshold voltage VT2, we say the device is turned on. So in the reverse manner, when the gate to source voltage goes below threshold voltage, we should be calling it as turned off. But what happens is there's a typical scenario that happens whenever your gate to source voltage goes below threshold voltage, and it is this thing that you see a small amount of drain current still flows from source to drain even before the gate to source voltage goes below threshold voltage. So whenever we say a device is turned on, it actually means that there is a finite amount of current flow from the source to drain. That's what we actually mean. That's why you see this current increase, the current is increasing in a positive direction, and there is a huge increase in the current whenever your gate to source voltage exceeds the threshold voltage. So in a reverse way, whenever your gate to source voltage goes below threshold voltage, it comes down, but somewhere near threshold voltage you still see a finite amount of current which is still flowing between source to drain. So this is called as leakage current or sub threshold current, and this also leads to a wastage in power. So what we'll do is we'll try to look into a device whose threshold voltage is located somewhere over is not located somewhere over here, but is located somewhere over here and located somewhere over here. We'll look into two cases of two NMOS devices with varying threshold voltage. Let's try to look into that. So for example, let's say we have a device whose threshold voltage is not VT2 now, but it's VT1. So in that case, and the VT1 is very close to zero voltage. So in that case, what happens is whenever your gate to source voltage goes below threshold voltage VT1, you still see a finite amount of current that is flowing from source to drain, which is true. But even if the gate voltage is turned exactly to 0 volts, basically we say that the device is completely shut off. During that point also, you see a finite amount of current that is being flowed from source to drain. So there is a huge amount of leakage for in a device which has got a threshold voltage of VT1. On the other hand, if you see, by the way, there are reasons for this flow of current below the threshold voltage, and there are device physics related reasons that are responsible for this kind of current. Basically, let me brief you about it. Basically, whenever we say that there is a flow of current from source to drain, what happens exactly is when you apply a gate voltage, there is an amount of inversion charge density that gets created. Basically, it's nothing a platform that's get created between source to drain. So that platform helps for the current flow from source to drain. And whenever your gate voltage goes below threshold voltage, that platform is supposed to disappear, but it doesn't get disappeared. It doesn't get disappeared abruptly, but it gets disappeared gradually. So when it tries to disappear, in that particular moment, you see a small amount of flow, a small flow of current between source to drain. So that is basically called as the sub-threshold current, and that is the thing that is responsible for the current even below threshold voltage. So that is basically a brief concept. So we'll get into details of all this when we move into lectures of device physics. So there we'll be looking into details from an electron, from a channel point of view. Let's not look into those things in this videos where we are primarily focused on the clock tree synthesis. Let's look into another device, another NMOS device which has got a threshold voltage of VT3. In this case, what happens whenever your gate to source voltage goes below threshold voltage, you still see a finite amount of current, which is true, but eventually, gradually, when you move towards zero voltage, the leakage current is very negligible. It's close to zero. Basically, it is so less that you can even ignore it. You can tend to ignore it. So so with a device having got a threshold voltage of VT3, the leakage, there is a very good improvement in the leakage value, in the leakage power. Basically, the leakage power is very less with the device with high threshold voltage, in contrast to device with low threshold voltage. But there is a problem that you see, there is a problem that is associated when you use a device, you use a NMOS or PMOS device with high threshold voltage, and the impact is that it impacts the performance directly. So this device takes a long time to turn on because the threshold voltage is located somewhere over here. So it takes this complete time to turn off on this device, and as a result, the timing of that cell, or the delay of that cell, is very bad. So that is one of the disadvantages of having a threshold voltage which is somewhere located in VT3. On the other hand, when you use a device with a threshold voltage VT2, the device becomes very fast. It becomes sufficiently fast, but again you see a problem of leakage current that is present over here. So VT2 is an optimal number that is very optimized for the performance and for the leakage power. So VT2 is an optimal number. So is an optimal threshold number for a device. So let me just brief you about, when we talk about threshold voltage, what is that? But what is that point? That is, what is that threshold voltage? So let's say this is an NMOS device what we have. So NMOS has got an N plus source which is located over here. It has got an N plus drain which is located over here, and this is the gate oxide and the polysilicon gate. So gate is connected to a voltage VGS. So basically, when we say VGS, it is this potential that we are trying to tune. Source is connected to ground, drain is connected to VDD. So when we say that threshold voltage, the threshold voltage is that amount of voltage, that amount of gate voltage at which you see this semiconductor surface inverts to an n-type material. So when we say it inverts to an n-type material, why we say that? Because in case of an NMOS, the NMOS is built on a p-type substrate. So inside a p-type substrate, you have an area which is completely n-type, and the point of voltage at which this phenomena occurs, that voltage is referred to as threshold voltage. So this was the platform that I was talking about in some time back, and you see a current flow from source to drain. So current flows from source to drain through this channel. There is a channel that gets created at threshold voltage, and this channel increases when you increase your gate VGS voltage, basically when you increase your gate voltage, and that is the reason for the flow of current that you see whenever you increase your gate voltage beyond threshold voltage. So ideally, when you reduce the threshold voltage when you reduce your gate voltage below threshold voltage, this channel should disappear, but that doesn't happen. That doesn't happen abruptly, but that happens gradually. Something like this. Let me show you. It happens gradually. So as a result of this, you see a small flow of current that happens whenever your gate voltage goes below threshold voltage. Basically, what happens whenever you see a source to drain current? So this part of the channel is depleted of the electrons, and this part has got more number of electrons. So basically, there is a concentration gradient over here. It's very similar to a bucket, which is let's say this is one bucket and this is the another one. So this bucket is completely filled with water, this bucket is empty. So you see a flow of water from the high amount of water to the area where the water amount is very low. Basically, it's a waterfall. Why there is a waterfall? You see a waterfall whenever there is a section which has got a huge amount of water, and it is connected to another section which has got a less amount of water. So to even out, so to balance out the water level, there is a water flow. Similarly, there is an electron flow due to the concentration gradient of electrons over here. So this is basically called as the diffusion current, and we'll be looking into all this in the separate section where we'll be talking only about the device physics, the threshold voltage, diffusion current, drift current, all those things. So let's not try to deviate ourselves from clock tree synthesis. So this is a concept that is related to the sub-threshold current, all the leakage current. But in this video, in this set of clock tree synthesis that we are actually doing, basically for this particular tree, we won't be using the concept of leakage current. Basically, we won't be changing the threshold voltage of all the cells that we are already been using. We'll keep the threshold voltage as VT2, as we just discussed in this video. So we will assume that the threshold voltage for all the devices, all the buffers over here is VT2. We'll assume that, and based on the concept of that we learned in the previous video, that is the short circuit current and the load capacitance, we will see since I'm running out of time, in the next video what we'll see is how the tuning of the load capacitance, or how, and we control the short circuit current, and hence the combination of these two concepts leads to a better number of buffers, leads to an optimal number of buffers. So we'll see how to reduce the number of buffers based on the concept of load capacitance and short circuit current in the next video. So let us try to look all this in the next video. Thank you.